Hello, I'm Dong Kim, PhD student from DGIST. Today I'll talk about 8x8 programmable multi-beam pattern projection based on multicast silicon photonic MEMS switches. Beam steering devices get a huge attention for LiDAR, free space communication, and others. Rotating motor and micrometer are widely used, but due to their limitation like size, speed, solid-state beam steering devices are needed. We can see the two mechanisms of on-chip beam steering. The optical phase array is widely researched, but they need a precise control of all array and it have an initialization problem. A trade-off between the array size and the beam divergence is also a problem. We can solve these things by using a lens-based approach. A beam divergence and a field of view are determined by the focal length of the lens. So we can choose a proper lens set for purpose. And the lens-based steering devices need well-performing optical switches. These are the previously reported lens-based beam steering devices. The left one shows the 4x4 2D array emitters, but use a summer optic method for the switch. It leads a high power consumption, so it is hard to scale up. The right one shows the 20x20 arrays and it uses MEMS switches. Silicon photonic MEMS switches give us a fast tuning speed, low optical loss, and low electrical power. It can be a solution for programmable photonics or large-scale switches. As we mentioned in previous slide, the 20x20 focal plane beam steering devices use MEMS switches. But it has a limitation that it can emit only one beam at a time. Here we demonstrate a programmable multicast beam steering device. Our device can perform a multi-point selective beam emissions. The programmable beam pattern generation allows us a fast acquisition and tracking of 3D point cloud and the multicast free space communication. Multicast switch is the key point of our device. It split a live power to multiple ports by partially turning on MEMS coupler. In my PI's previous work, the multicast switch is demonstrated, but there are some excess loss due to unicell configurations. Here is the basic architecture of our device. There are 1x64 MEMS multicast switch array that is improved design to eliminate excess splitting loss. Each drop port of the switches is terminated with a grating coupler. 8x8 64 grating couplers are placed. The pitch of the emitters are 45 by 50 micro. Let's see the details of the switch unicell. The left figure shows the microscope image of the switch unicell. The coupling ratio between the through and drop ports is controlled by the MEMS tunable directional coupler. As shown in the right SEM image, there are two waveguides located in parallel. One of the waveguides is attached to the MEMS actuator. The vertical location of the attached waveguide is controlled by the actuator. By changing the vertical displacement of the waveguide, we can control the coupling ratio of the directional coupler. The right figure shows the simulated response of the tunable directional coupler. As we can change the coupling ratio 0 to 100% analogically, by changing the vertical displacement of the MEMS actuator. The length of the coupler that we use is 100 micrometer, and by only changing 1 micrometer of vertical displacement, we can have full tuning. This slide shows details of the working mechanism of our MEMS actuator. We utilize the electrostatic cantilever type actuator, which is shown in the left figure. The cantilever is initially lifted about 1 micrometer. The cantilever is brought down by the electrostatic force between the cantilever and the substrate when bias voltage is applied. We characterized our switches. The left figure shows the time response of the switch unit cell. It takes about 10 microseconds for one cycle's on and off operations. It indicates that our optical power distribution network can be reconfigured 10,000 times per second. The right figure illustrates the optical power response to drop pots when bias voltage is applied. It shows an analogical response, and we achieve a maximum power coupling ratio when 8 voltage is applied to the actuator. Then we measure the emitted beam from the grating coupler. To measure the beam pattern, the lens whose focal length is 4 mm is placed above the emitter array. Then additional lens set is located to observe the projected beam with an IR image sensor. The right figure shows the beam divergence profile. 0.08 by 0.09 degree beam divergence is measured. Beam projection also measured. These patterns are not an overlay image. The field of view of our system is 4 by 4.6 degree. First, we make all the switches on state, and we clearly see that all 64 emitters are operated properly. Let's make some patterns. By programming the switch configurations, we can achieve some uniform patterns. The red dot indicates the on-state switches. Then what about arbitrary pattern projections? By just changing the switch configurations, a simple shape pattern projection is performed. For summary, we demonstrate the 8x8 programmable multi-beam pattern projection based on multicast silicon photonics MEMS switches. MEMS switches give us a relatively low power consumption and fast operation speed. The divergence of the emitted beam is 0.08 by 0.09 degree. The field of view of our devices is 4 by 4.6 degree. Now we are trying to scale up our devices and demonstrate the monostatic operations. This work has been done by collaboration with Professor Gyeong-sik Yu at DGIST and Professor Kwak at EPFL. This work is supported by Samsung Science and Technology Foundation. Thank you for listening.